People who have doesn't rename your names usernames as a proper way, please rename your names. First your registration number and then your names. I can see that few of you haven't renamed your names in the proper way. Okay, now let's start the practical again. So in procedure part 1, you have to generate in a frequency modulated wave. Okay, you have to generate a frequency modulated wave and determination of VCO constant. Okay, so in this section you have to see how to generate a frequency modulating wave and to determine the VCO constant. Okay, this is the circuit you have to implement in the modulation board, and here they have given different DC voltage levels and you have to measure the output frequencies. Okay, so as an information signal we can give different DC voltage levels to this VCO circuit, and then we can see what is the output frequency. Okay, what is the frequency of the output signal. So let's see how to do this. Okay, here you can see this is the circuit as in your figure. It is the VCO circuit we are going to use to generate a frequency modulated wave. So we can give input here and we can take the output from here. Okay, so let's see how to do our practical. So I am giving the input to the circuit, and you can see here this is as in your lab sheet. We are taking the input from the 2.5 volt plus and minus. Between that range we can give DC voltage levels to our circuit, and from this knob we can change the voltage level. So by using this knob we can change the voltage and see what is the output frequency. So I am taking the output from here. And I connect the ground pin. Here is the ground. And I'm connecting the oscilloscope to the output signal to see what is the output signal. So now I am connecting the multimeter to the input signal because we want to see what is the voltage level, to make sure the voltage level. And I'm connecting the ground. you can see the output waveform. So when we are turning this knob, we can change the voltage. So you can see that when we are turning this knob, the voltage, DC voltage is changing. Okay, first in the table number 1, we have to make the voltage into minus 1.5 volts. Okay, so now here you can see that it's approximately minus 1.5 volt. Okay, so now let's see what is the output frequency. Okay, so this is the output waveform, and you can read the frequency from the oscilloscope. I'll stop it. Okay, you have to note down these frequency values. Then for the next one, we have to make the voltage minus 1. You can see that when we are increasing the voltage, the frequency is increasing. Okay, now it's minus 1 volt, and you can see the frequency. You can note down the frequency value of the output waveform. Okay. Then we have to make the voltage, input voltage, to minus 0.5. Now it's approximately minus 0.5 volts. So you can see what is the output frequency. From here you can see what is the frequency. Then we have to make the voltage, input voltage, to 0. Okay, now the voltage scale here becomes millivolt. Okay, so when we are increasing from minus to plus voltage, nearly in the 0, it becomes millivolt scale. So this displayed in millivolt scale. You can't see it here. So we can consider this as approximately 0 because it's 32 millivolts. Let's see. Okay, it's approximately 0. So let's see what is the frequency value. Okay, then we have to make voltage to 0.5. Note down the frequency value for 0.5. Now we have to make voltage to 1 volt. Then let's make the voltage to 1.5. So then we have to make the voltage to 2.0. It's 2 volts. Okay, then for the final reading, we have to make the voltage to 2.5 and see what is the output frequency. Okay, that's the very first part. So have you all note down the all the readings? If anyone missed any reading, please let me know. Uh, so in your lab sheet, you have to in your lab reports, you have to note down, fill the table 1 from these readings, and you have to draw the graph between frequency and input voltage, and you have to determine the VCO constant by using the slope of the graph. Okay, do these things in your lab reports. So then you are saying in your lab sheet, here input sine waves with frequencies 2 kHz and 1 kHz separately to the VCO and observe the output waveform. So now we are going to input two sinusoidal waveforms as information signals and see the frequency modulated waveforms. Okay, so now let's move on to the practical. You can see that we can give 2 kilohertz input from here. 2 kilohertz. 2 kilohertz is the frequency of the information signal then. So we can give this input from here to the VCO circuit. And we can take the output from here. So I am taking the input from here to see the input waveform, okay, to connect the oscilloscope. It can be taken by connecting here or here or here, okay. So then I am connecting the channel 1 of the oscilloscope to the input signal. And channel 2 of the oscilloscope to output signal. Testing the waveform here. From yellow color you can see the channel 1 signal, that is input signal, and in blue color you can see the output signal in blue color. For channel 2, it's in channel 2, okay. I'm increasing the voltage here from this knob, because when we voltage is increased, you can clearly see the modulated waveform, because the frequency will be increased. So here you can see this waveform is modulated, frequency modulated waveform. You can see according to the voltage variation of the information signal, the frequency is variated in the modulated signal, okay. So this is the modulated output signal. I saved all these waveforms, and I'll give you these waveforms. After each part, I'll put the waveforms in your chat, so download them. And I didn't rename them in the relevant names, only I named them with numbers, okay. So please see what are the waveforms for relevant parts, and download them and add your reports, okay. So now I am going to change the input signal to 1 kilohertz, okay. We have checked the modulated signal by giving the 2 kilohertz input signal, information signal. Now we are giving another information signal having a frequency of 1 kilohertz. Okay. Here also you can see the modulated waveform, the variation of frequency according to the information signal. Okay, so I think you will have seen the two waveforms. Okay, so now I am going to put the two waveforms in the chat. Please download them. Okay, have you any questions or unclear thing or any missed reading in the first part? Okay, if not, we can move on to the next part. If anything, you can tell me. If there's anything, you can tell me. Okay. In this part, you have to measure the frequency deviation and modulation index. Okay. So this is the circuit you have to connect, and then for these three frequencies, sorry, we have to give these two voltage inputs separately. Okay, at once we have to give 0.25 voltage, and then we have to give 0.5 voltage for all the three frequency values, information signal frequency values. Then we have to check the output frequency, what is the maximum frequency and what is the minimum frequency. Okay, then you can calculate the frequency deviation by considering these two values, and you can calculate the modulation index also, because you already know the information signal frequency. Okay, then you have to draw some graphs, and I have to mention when we are doing this part, we are doing this part also together. Okay, so this part also we have to implement the same circuit, and they say we have to maintain modulation index greater than 1 while performing the following. Okay, and they then say to keep the amplitude constant and change the frequency, and then keep the frequency constant and change the amplitude. Okay, here amplitude is the voltage value because it's a voltage signal. So these are the three values they are given: three voltage values and three frequency values. Okay, so here in the previous table also we have given the same frequency, 3M frequency values, 500, 1 kilohertz and 2 kilohertz for these two voltage levels. And the next here we have given 200 millivolts, 0.5 volt and 1 volt. Okay, so here we can consider this as 250 millivolts, 0.25 volts. So it's same as before because it's very close values. So we are going to see the frequency spectrums for these two tables at the same time, because we have to check newly values for this 1 volt only. So we are going to do all the values at the same time. Okay, if you don't understand, please ask me. I'll describe you while doing the practical. Like this, we are going to give one frequency value for by changing the voltage to 0.25 volt, 0.5 volt and 1 volt. Okay, then we can check what is the F max and F minimum. Okay, you have to fill the graph only for this these values, but you have to observe the frequency spectrum for the next part. Okay, these all the values. Okay, so let's move on to the practical. So I'm going to describe you while doing the practical, and you have to note down the values for table number 2 also. Okay, if you don't understand while I'm doing the practical, please let me know. Okay, first we are going to give the 500 hertz input. We are giving the VCO circuit. We are giving the input to the VCO circuit, and we are taking the output from here as same as before. Then we are connecting the oscilloscope to the input signal, because we have to check the voltage value. Then to measure the frequency values, I connect the spectrum analyzer to the output pin. So from here, you can see the amplitude value of the input signal. Okay, here voltage of the information signal, U information equals 0.25. Okay, that means the amplitude of the input waveform. So we have to make this amplitude to 0.25 volt. That means 250 millivolts. Okay, now by turning the voltage knob, we can change the voltage into 250 millivolts. Okay, we are keeping here. So you can see the input waveform, a sinusoidal waveform with 500 hertz frequency and 0.25 volt voltage. Then this is the spectrum for output signal, frequency spectrum. You have already familiar with spectrum analyzer because for the previous practical, I think you have used the spectrum analyzer. So here for having a clear picture of the spectrum, I am change the start and stop frequencies. So without more noise, we can see the spectrum. So now I am going to measure the, see this marker, we can make this marker to these peaks. So we can see the frequency from here. And remember here, when this magnitude value becomes lesser than minus 20, it can be considered as a noise. Okay, so when we are measuring the frequency values, always we have to consider only about the values higher than minus 20. Okay, this value, this magnitude value should be higher than the minus 20 dBm. Okay, so let's see what is the maximum frequency. You know, this is a frequency axis, so maximum frequency is here and minimum frequency is here. So now we are going to measure the maximum frequency. Here you can see this is minus 34 point something. So it's noise. It's a noise. It can be considered as a noise, not our required signal. Okay. Here it is approximately minus 20. So we can take this value. So you can note down the. Sorry, I'll see you again. So you can note down this value as the maximum frequency. Okay. Then let's see what is the minimum frequency. Here we have to take this value as the minimum frequency. So please note down this value. This is for 500 hertz input and for 0.25 voltages. Okay, voltage. So in table number 2, note down these readings. Okay, I save the waveform. Now this is in 500 input. Okay, so we check the output signal for 0.25 volts, and now we are going to see the output signal for 0.5 volt. You can see that these are with very lesser magnitude values, so we can't get these things as frequency values, we required frequency values. Okay, I'll show you again the two frequency values. You can
Madam,
write down. Yes.
In order to take the minimum and maximum frequency, so it means that the amplitude dBm value less than -20. Uh, if the value less than -20, that means take the peak as the value that we require, isn't it? Or
Uh,
we can
I
take it.
can't get. It means if this value is lesser than -20, that means my -30, -40, or minus something value. It is considered as a noise. Okay, so we are considering only the higher dBm values than -20. Okay,
Okay.
so we are considering only that range. So from that range, we can check what is the maximum and minimum frequencies. Okay, you got that?
Okay, madam. Okay,
Okay.
thank you.
Okay, so here you can note down this as the minimum frequency. Let's see what is the maximum frequency. Here you can see that this is -25. Okay, that is lesser than -20. Okay, that means this can be considered as a noise. So we are not considering this frequency value. Okay, so let's move to the next one. And here it is -16, so it's higher than -20. So we can take this as the maximum frequency. Okay, so now we checked 0.5 voltage input for 500 hertz and see what is the maximum and minimum frequencies of the output signal. And now we are going to change the voltage to 1 volt. It's not here in this table number 2, but for the next section you have to observe the waveforms for 1 volts also. Okay, so now we are going to check the 1 volt amplitude and 500 hertz input signal. What is the output? Okay, here you don't have to fill the table, but just note down the frequency values and calculate and check whether the beta is higher than 1 or lesser than 1. Okay, and observe the frequency spectrums, waveforms, and I'll give you the waveforms at the end of this part. Okay, so I am increasing the voltage to 1 volt. The amplitude is changing here, you can see. we can't get this value, so we are getting this value as the maximum frequency. Okay, this value is the maximum frequency. We are considering from here, the frequency range from here. Okay, these things can be considered as noise. Okay. Okay, now here we kept the frequency at 500 and we vary the voltage from 0.25 to zero point 0.5 and then for 1 volt. Okay, for all the three voltages values, we check the output waveform for 500 hertz input signal. Okay, then now we have to take the 1 kilohertz input and check output signal for 3 voltage levels. Okay, now I connect the input to the 1 kilohertz signal and we have to make the amplitude to 0.25. Here you can see that amplitude is approximately 250 millivolts. So now see how is the output waveform. So here this can be considered as the minimum frequency. Now let's see what is the maximum frequency. Okay, I hope all of you have noted down these values. So now I am save the waveform. Okay, now I am changing the amplitude value to 0.5. It's 500 millivolt. We are checking this for 1 kilohertz input. Okay. Okay, you can note down the maximum frequency value. It is very close to -20, so I take this as the minimum frequency. Uh, so now let's increase the voltage to 1 volt. You can see the frequency is 1 kilohertz and the amplitude is 1 volt. So this is the spectrum for 1 volt. You can note down the maximum frequency value. Here you can note down the minimum frequency value. Okay, now we check we keep the input signal in 1 kilohertz and change the voltage to 0.25 volts, 0.5 volts and 1 volts, and check what is the maximum and minimum frequencies of output signal, modulated signal. Okay, so now we are going to change the input frequency to 2 kilohertz. For 2 kilohertz, we are changing the amplitude to 250 millivolts. We can take this as the maximum frequency. So we can't get this value because this is lesser than -20. So we are taking the next peak. Okay, this peak. So you can note down the frequency value. And we are changing the amplitude to 500 millivolts. Then let's see how the waveform is here. This can be considered as the maximum frequency. I'll show you again if you want. Okay, if you couldn't note down, please note down. This is the maximum frequency. Then let's see what is the minimum frequency. We can't get this peak, so we are taking this peak as the minimum frequency. Okay, please note down. Okay, so finally we have to make the voltage to 1 volt. Here I can't see the whole spectrum well, so I am changing the start frequency and stop frequency values so I can clearly see the spectrum. So we can consider this as the maximum frequency. Let's see what is the minimum frequency value. This can be considered as the minimum frequency value. Okay, so these are the calls for part 2. Here which give input signal in 500, 1 kilohertz and 2 kilohertz. For each frequency input, we change the voltage from 0.25 volts to 0.5 volts and then 1 volt. Okay, so for table number 2 you can fill all the frequency maximum and minimum values, and you have to calculate the frequency deviation and modulation index. So then you have to draw the graphs between frequency deviation and information signal voltage, and modulation index was information signal voltage. Okay, so fill this table and draw the graphs, and in next part I'll show you in the lab sheet. Okay, for this table, you can fill with the note down values, and you can draw these two graphs. Okay, so in this part, this can be considered as the values, same values for 250 millivolts we have taken. So then, for 1 volts also, calculate the beta values and check it is lesser than or higher than 1. And all the spectrums saved waveforms you have to add to the reports. I'll give you the waveforms because you have to observe the spectrum for each case. So it's for 500 hertz for this voltage, 500 input for this voltage. Likewise, you have to add all the 9 spectrums to the report. Okay, I'll put them in the chat now. So did you understand how to do these two parts, or are there any unclear things? Okay, I'll put the waveforms later, so we can move on to the next part. First, I think it's better if I put the waveforms now. So wait a little bit. I'll put the waveforms into the chat.
Excuse me, madam.
Yes.
Madam, in when we are getting the frequencies in the left
Yeah.
side of the spectrum analyzer, we got the minimum frequencies, and the right side of the spectrum analyzer, we got maximum.
Yeah.
Is there any particular reason to get like that?
Yeah, this is the spectrum analyzer. So here in oscilloscope, I'll show you. In oscilloscope, we have the here the time axis. Okay.
Sorry, madam, we cannot see.
You can't. Oh, okay, sorry. I'll show. Okay. Now can you see?
Yes, madam.
Okay. In oscilloscope, we know that here we have the time axis, and here we have the amplitude axis. Okay, voltage values here, and the time axis here. But in this is spectrum analyzer, so this is the frequency axis. So here like as the time axis, this is the frequency axis. So when it gets to the right side, the frequency is increasing. From here to here, frequency is increasing. Okay, because this is the frequency axis. Do you understand?
Okay, madam. Yes.
Okay. Okay. Then let's move to the next part, and I'll put the graphs into the chat while doing the practical. Okay. Okay, in the part 3 of the practical, you have objective of this section of the laboratory is to generate a frequency modulated signal using a signal generator which bears the following characteristics. Okay, so they have given the carrier frequency, power level, FM frequency deviation, and FM rate values. So we have to give these values. Mahisha. Uh, who is Mahisha now? Entered someone.
Excuse me, madam.
What is your name?
No, I'm Shimla.
Okay, okay. You can rename your name. Okay. So we have to give these values to signal generator and make a frequency modulated waveform and see that from oscilloscope. Okay, and spectrum analyzer. Okay, for our practical, we are going to use a function generator for that. Okay, so now let's move to the third part. Here, this is the oscilloscope, spectrum analyzer, and function generator. Okay, we are using these to generate a frequency modulated wave by giving the signals with the relevant values. They have the given values in the lab sheet. Okay, so we are connecting all the three together. So oscilloscope, spectrum analyzer, and the function generator all are connected together. So I turned on it. Here we can put whether we want a square wave or a pulse wave or a sine wave. Okay, we want sine wave, so we can sine wave. And here we can make the carrier frequency as 100 kilohertz. Okay, so we give up the carrier frequency as 100 kilohertz. And so in your lab sheet, in the next page, they have given the amplitude as 0.1 volt. So that is what we have given 100 millivolt peak to peak voltage value for amplitude. So we are giving frequency modulation. So FM rate is, that means FM frequency is 1 hertz and the deviation is 6 kilohertz. So we have given all the values they have given. So this is turned on, and now we can see the waveform from the spectrum analyzer. So let's see. from spectrum analyzer, and here in the oscilloscope you can see the FM modulation, okay, frequency modulated wave. Okay, the frequency is changing. This is the waveform. So this is the spectrum. So I give you the waveforms all together. So can you see the waveforms here? So in this part, we generated a frequency modulated wave using a signal generator, and we observed the waveform from the oscilloscope and the spectrum analyzer. Okay, so here you just had to add the two waveforms to the report. So I'll give you the waveforms. And before move on to the next part, say something about FM demodulation. Okay, can anyone tell me frequency demodulation techniques that you know? Any?
Envelope detect.
Sorry?
Envelope detect.
Okay. Any other one? Another one?
Current detection.
Sorry?
Current detection.
I can't hear you.
Current process detection.
Okay. I can't hear you well, but it's okay. So, who is this?
Madam, can you hear me now?
Yes.
Okay, I said Costa's regressive with that current detection using.
Okay. Okay. Good. Let's see what are the techniques we have to learn today. Okay. So here it's Gunavardhana. I think you have a power issue, something. No? You can remain another 20 minutes.
Yes.
Okay. Remain until then. We have another few things to do in the practical. Okay. So we talked about modulation, and in demodulation, you know that when we set a modulated signal in the receiving end, we have to demodulate it to take the original signal. Okay. So like this, when we send a modulated signal like this from using a demodulator, we can take the information signal. Okay. So here in your lab sheets, we have to learn about few demodulation techniques. One is slope detector and differentiate envelope detector. From this we can give the frequency modulated wave here, and using a slope detector we can have a waveform like this. Okay, that means it's like a amplitude modulated waveform. Okay, but here the frequency modulation also can seen here, and by using envelope detector finally we can get the information signal. There can be some variations due to some distortion, some noises or things, but we can have a information original signal like this. Okay, uh, and the next one you have is zero crossing detector. I think you have learned them in your classes because these are the things in your lab sheet. So okay, you have to learn. Here zero crossing detector, if we are given a frequency modulated signal like this, it considers the zero crossing points, and finally it gives the pulse wave like this. Okay, according to these frequency variations, pulses are also show us that. Okay, so like this pulse signal can be seen. Okay, by making this using a low pass filter, by using a filter you can finally get a sinusoidal wave. Okay, so we are going to see this scenario also from using the count detector today. So here you can see if this is the modulated signal, you can get a waveform like this. And then finally you have the phase lock loop circuit. Here also can be used as a demodulation, used as a demodulator. When we input a frequency signal, we can get a information signal. If you want, in our demodulation board circuit, if you want, we can get a digital output, that means with pulses, or we can get a sinusoidal output. Okay, so let's now move on to the practical. Okay, in the lab sheet, for doing the practical, have to see the lab sheet. In the lab sheet, first you have to use the C discriminator circuit. Okay, so here you have to feed the modulated signal to the C discriminator circuit in the demodulation board, and you have to observe the output waveform. Okay, then let's see what is the output of the waveform. Okay, so this is the discriminator circuit. Okay, this is in our demodulation board, and then you have to give the modulated input to count discriminator circuit and see what is the output, and finally you have to give the modulated signal to the PLL circuit, phase loop circuit, and see what is the output. Okay, so now let's do the practical. Okay, first we have to make a modulated signal from modulation board, because we have to give a modulated signal to the demodulation board. Okay, so we are giving a 2 kilohertz information signal and making a modulated waveform using the VCO circuit, and give the modulated signal to the C. Here you can see this is the C discriminator circuit. Okay, we give this input to here. So this is connected to see the input signal, and we are taking the output. Okay, so I am connecting all these to oscilloscope. Before that, we have to make common ground, common the two ground pins, and take the ground to connect oscilloscope. So for channel 1, I am giving the modulated waveform input to the demodulation circuit, and from channel 2 we can see output. Okay, so here you can see this is the modulated signal. So you can see the frequency is higher here, frequency is lower here. This is the modulated signal, and this is the output we got from the C discriminator. Okay, so it is as the slope detector. When the frequency is low here, it is becomes low. Okay, frequency high becomes higher. It's like amplitude modulated waveform. Okay, we can take this output from the C discriminator circuit. Then in your lab sheet it says to connect the output of the C discriminator to the AM demodulation circuit in the demodulation board. Connect the second input to summer component by bypassing the line with the connector node. Okay, so we are taking the output from C discriminator and give it to the input here, AM demodulation. Okay, so this is the AM demodulation circuit you can see here. So I give the input to here taken from this output, and this is the summer component. Here I use a pin to connect these two, so we can take the output from here from AM demodulation. This is so because we got the amplitude modulated wave, so in order to get the information signal, we have to use the amplitude demodulation circuit. So now I am connecting this as the this is to channel 2. Here you can see the information signal is here. Okay, I will show you again. Okay, according to this frequency modulated wave, we got the information signal. You can see here the frequency is 2.019 kilohertz for this wave. Okay, channel 2 wave. You remember that we given 2 kilohertz input to the modulating as information signal to the modulated circuit. So we are taking the output as the information signal, okay, as same information signal with frequency of 2 kilohertz. Now we have to use the count discriminator. In the next part, you have to input the modulated signal to the count discriminator circuit and record the waveforms. Okay. So here is the count discriminator circuit. So I give the modulated input to here and taking the output from here. So if we when we zoom this waveforms, we can see there's a pulse wave here. As we show in the as we seen from the zero crossing detector circuit, according to the modulated waveform, there's a pulse wave. Okay, according to this frequency, you can see the distance between the pulses are also varying. So finally, we have to input the modulated wave to the PLL circuit and put the radio button to the FM and observe the waveforms. Okay, so now we are giving the modulated from to the free here you can see it's you can here it's marked as PLL. Okay, so we give the input here and this is the radio button, so we can use it for phase shift keying or frequency modulation. So now we are considering our FM, so we are put this button to decide. Okay, here you can see if we take the output from here, we can see what is the waveform. Here you can see it's pulse waveform. Okay, digital waveform is here. So, but we are going to observe the information signal. So we are connecting the circuit to the next input. Okay, next output. Here also you can see, according to the frequency modulated wave, we got the information signal. The frequency here is 1.926. Okay, it's very close to 2 kilohertz. So we given a 2 kilohertz information signal. So we got the demodulated information signal. There are some distortions, but we got the information signal. Okay. So this is the final part of the practical. So I hope that you understand, you saw the demodulation waveforms well. So if there's any issue, please tell me. Okay, let's move to the report. Okay, we have done 4 parts to the in this practical. Okay, in the discussion, you have to answer for 3 parts. I think you have in your lab reports, you have enough space to write the answers. Okay, so write the discussion part at there. And when we talk about the report from the beginning, okay, do your pre-labs. I hope that already you have done the pre-labs. And here you have to fill this table with the note down values and draw the graphs and find the VCO constant. And then for this number 6 procedure, you have to add the 2 waveforms we observed for the first part. I'll already put them in the chat, so download them. And this part, for this part, you have to fill this table and find by finding the delta F and beta values and draw these 2 graphs. And for this one, you have to add the all the spectrums we observed for all these 3 values. Actually there are 9 spectrums, because we are varying frequency by keeping varying amplitude by keeping frequency constant likewise. Okay, so you have to add the spectrums for these things. And for 1 volt values, please calculate the beta values and check whether it is greater than 1 or not. Okay, so for this one, part 3, we observed the generated frequency modulated wave from the oscilloscope and the spectrum analyzer. So add the waveforms to the report. And for the final part also, we observed 4 waveforms. Add them to your reports. Okay, so this is the end of the practical. So now I will put the waveforms to the chat. Okay. Okay, there is some issue with sending these figures, so I'll send these figures to your batch rep. Okay, so you can share the waveforms with everyone. Okay, so are there any problem before we wind up the session? Do you have any problem? Okay. Seems that you don't have any issues and you understand the practical, so I'll share the waveforms with your batch rep. Okay. So you can take them and make your report. So submit your reports within 7 working days. So then I'll stop the practical. Uh, okay, I'll stop. Thank you for all.
Please wait.
Masar, please stay.